go to the, it's a video on squares, the square of a Vedic math way. It's video number 12. It's a video on squares, and we will square of numbers, integer numbers. It's Vedic math way, video number 12. Let's continue. Okay, let's continue. The next section we would discuss squares of numbers ending in 5. Let's continue here. Look at how do you do that. A number ending 5 is given by 10 times n plus 5. These are numbers like n equal to 10 times n plus 5, and if I do a square of that and n squared, it is a plus b, and square of that is a squared, which is 100 n squared, plus 2ab, which is 100 n, plus b squared, which is 25. Let's continue here. So which is equal to, if I extract 100 n from the first two terms here, I get 100 times n times n plus 1. So if I'm trying to extract n plus 1s from here, I get 100 n plus 1. Okay? And then 25 is plus 25. Okay, so that is equal to n times n plus 1 and 25. We're trying to exploit place value systems here, because we are going to shift the left part by 2 to the left, which is multiplying by 100. Okay, so we usually say that on left I get n times n plus 1, which was the, okay, and then 25 on the right. Okay? And which in fact I mean is, on left it's 100 times n plus 1 plus 25. That's the answer. And so this is the correct answer here, 100 times n times n plus 1 plus 25, and 25 has 2 digits. If I multiply some number by 100, we get a 2 zeros at the end, and this 25 added slides right into those 2 zeros. So I can say that add 25 on the right and n times n plus 1 on the left. So okay, that's, we are trying to exploit place value system here. Okay, let's continue here. Note, if n is 11, then n square is 100 times 11 times 12. Okay, if it's, we are trying to do a square of 115, so that is plus 25, and that is 13200 plus 25, that is 13225. That means that 115 squared is 13225. Let's continue. On the left, it's by 1 more than 1 before. This is the sutra we are going to use here. So this is, n was the original number on the left. We say n times n plus 1 by 1 more than 1 before. On the right, it's 25. Let's continue. Some examples now. 15 times 15. On the left, it's 1. 1 times 1 plus 1 is 2. And on the right is 25. So 15 times 15, 15 squared is 225. Okay. Next, another example, 75 times 75, which on the left it's a 7 times 8. 8 is by 1 more than 1 before of 7. And on the right, 25. Answer is 5625. Continue. Example, 135 times 135. On the left, it's 13 times 14. 14 is by 1 more than 1 before of 13. On right is 25. And answer is 18225. Let's continue. 65 times 65. On left, it is 6 times 7. 7 is 1 more than 1 before of 6. And so answer is 4225. Let's continue here. 245 times 245. 245 squared is on left 24 times 25. On the right is 25. It's a 625. Let's continue. 35 times 35 is 35 squared is on left is 12. On right is 25. 1225. 985 times 985. On the left is 98 times 99. On the right is 25. And so 98 times 99 is 9702, and 25 on the right. Note, use basic base multiplication. This I used that to get 98 times 99. I can use the base multiplications we studied before, and that's the video for. Let's do some examples here. So do a fraction now. 0.25 times 0.25. 25 times 25 is 625, and there are two digits here after the decimal, two here. So I need to have four digits after the decimal. So that I need extra zero here. So 0.0625. 20.25 is quarter. 0.25 is quarter. So 1/4 times 1/4 is 1/16th. So 1/16th is 0.0625. Let's continue here. We need four places after decimals. That's how come there's zero here. Okay. Up 0.25 is quarter. So there again, just the 1/4 times 1/4 equal 1/16, which is 0.0625. We just converted 1/16 to 0.0625. Okay, now 0.125 times 125, same way. It's on left is 12 times 13, and on the right is 25, and there are three digits here, and after here, so it's a 6. We have divided by 1 million here, and that is equal to 0.015625. 15625 from here, and 0 extra because 3 digits and 3 digits 6. I need 6 digits after decimal. These were 1, 2, 3, 4, 5. I make up that with extra 0 here. Let's continue here. 0.75 times 0.75 is 5625 after decimal. Okay, on left 7 times 8 56 and 25 on the right, and the 4 digits I need a 4, and 0.999 3 nines and 5 and 3 squared. Okay, so it on the left it's 999 times 1000, and on the which is 999 0 on the right it's a 25. So 0.9995 squared is equal to 0.393025. Okay. Exercises now. So 15 times 15 we already did before. 35 times 35, 45 squared, 55 squared, 65 squared, 75 squared, 85 squared, 95, 115, 125 squared, 145, and some more. Okay. Now some fraction. 0.25 times 0.25 we discussed already. 0.35 times 0.35, 0.125 times 0.125, 0.65 times 0.65, and some more. Okay. We're going to extend the method we just studied. Okay, here in this section we will consider product of two numbers such that neither of which ends in 5. Instead, sum of the digits on the right part is 10. On the right, sum is a base number like 10, 100, and 1000. So we would not be doing squares here. Okay, left parts are equal. Example is 23 times 27. So we are not doing square, but we are trying to use same method, which is by one more than one before. Okay. Here two numbers of this type are 10a plus n, and this is one number. Okay. Another is 10a plus 10 minus n. Okay, so n and 10 minus n adds up to 10, which is one of the base numbers here. Okay. Continue here. Here two numbers from previous page. N1 is 10 times a plus n, and N2 is 10 times a plus 10 minus n. Left part is constant, same, and right part is adds up to 10. N plus 10 minus n is 10. Let's continue here. N1 times N2 is first number, which is 10a plus n, times second number, which is 10a plus 10 minus n. 10a plus 10 minus n. Let's continue here. So we're going to multiply now. So I multiply 10a by 10a. I got 100a squared. I'm going to multiply 10a with the 10 minus n. This is what I got. 10a times parenthesis 10 minus n, parenthesis closed. Then I start multiplying with now n here. N times 10a is 10 times an, and I multiply 10 with it by 10 minus n, and that is the other term here. Let's continue. So we have 100a squared plus this term gives me 100a, and 10a times minus n gives me minus 10n. We had a plus 10an, and this is minus 10an, and plus 10an, and the last term was n times 10 minus n. These two cancel out, and from here I can extract out 100a as a factor. So this term is 100a times a plus 1. So we have extracted 100a of a plus 1 from here. And then last term is n times 10 minus n. See the 100 here? If this thing is the 2 digits, we can use place value system to say this is the left hand part of the answer and this is the right hand part of the answer. Let's continue here. So on left side is a times a plus 1. On right side is n times 10 minus n. If this thing, if there are only 2 digits in the right part, this is represent 100 times of a times a plus 1. So we would exploit place value system when we can, but we have to honor its rules. That means we have to replace 100 by left hand. Say we removed 100, say it's the left hand part, so that because we removed 100 from here, that dictates that we do need a 2 digits on. Let's continue the method here. So that means n1 times n2 is 10 times a plus n, and that's what the n1 times n2 was. Okay, so and this is the results was 100 times a plus 1, and on the plus n times 10 minus n. And 23 times 27 is 100 times 2. This is 2 right here. This was a, and this is the n, and this is 10 minus n. 2 and times 2 plus 1, which is it 100 times 2 times 2 plus 1 right here, and plus n, which is 3, and 10 minus n is 7. 3 times 7. Okay, so we get a 600 plus 21, which is a 621, and this is 6 on the left and 21 on the right. We can say that instead of 600 plus 21, we can say 6 on the left and 21 on the right. As long as there are 2 digits on the right, and that's covered by this 100 multiplier here. Okay? So 100 multiplier on the left, 100 is the base here, and that's 6 on the left of 2 digits. It is like 600 plus 21 like we need. Okay, let's continue here. So that means that is 2 times 2 plus 1 on the left and 3 times 7 on the right. This is a by 1 more than 1 before, like sutra we have been talking about. Sutra is by 1 more than 1 before. We had departed from doing squares, but this is important because this uh, multiplication also uses same sutra. Okay? And these multiplications need to go together with the square of numbers ending in 5. Let's suppose say 21 times 29 is 100 times 2 times 2 plus 1 on the left, 1 plus 9 on the right. Let's continue here. So it's 600 on left and 9 on the right, okay? Which is 609, and that's like 6 and 09. 6 on left, 09 on the right, and which is a 2 times 2 plus 1 is 6, and 1 plus 9 is 9. But I do need 2 digits on the right, so that would mean that instead of 9, I would need a 09 here. Notes. One right become on the right 9 becomes 09. Okay, we love to exploit place value system, and we also need to honor its rules. Okay, continue here. So either use 100 times 2 times 3 plus 1 times 9, or use 2 times 2 plus 1 and on the right 09. Okay, now 22 times 28, 24 times 26, 37 times 33, and some more. And these fractions now. 0.22 times 0.28, 0.998 times 0.992. Okay, let's continue. Here. So in this case, we'll consider example where left parts add up to 10 and right parts are equal. Let's continue here. So 3, 4 times 7, 4. On the left, it is 3 and a 7. They both add up to 10. On the right parts, they are equal. See, it's not a square, but it is goes along, use the same kind of method as is used in square of numbers ending in 5. Okay? So let's see what, in this case, product is 3 times 7, the parts on left plus the common part on right, and that's left part. On the right, it is 4 times 4. So either use 100 times that on left plus the right part, or make sure there are 2 digits on the right. Let's continue here. So it's 21 plus 4 on the left, 16 on the right. It's 25, 16. So it is on the left, it's actually 2500 plus 16, and because there are 16 has 2 digits, and we can say 25 on left and 16 on right. Continue. Okay, you can prove the assertion if you care to. Okay, and yeah, this thing works only for 2-digit numbers. If it's more than 2 digits, it doesn't work in exactly the same way as stated here. Okay, let's continue. 51 times 51, 52 times 52, those squares. Okay, 53 times 53. When it's 5 on left, these become squares. Okay, then 27 times 87, these are not squares. 43 times 67, 77 times 37, 68 times 48, 73 times 33, and more. Now fraction 0.23 times 0.83, 0.41 times 0.61, 0.76 times 0.36. Okay, and some more. Continue. Let's discuss references here. My first reference is usually this Vedic Math Teaching Volume Manual, Volume 1, which is a elementary volume, and it's by Ken Williams. You can get that in PDF form for free and print form for purchase from vedicmaths.org. Let's continue here. We can get a Vedic Math by Bharati Krishna Tirtha Ji is the main reference on the topic. Vedic Math for Schools in 3 volumes by James T. Glover is a good reference, and Glover used these books in his school. Let's continue. And Vanda Singhal covered recent topics in her book. Let's continue. And figuring is the reference for the first section here. Okay? Figuring by Shakunta Devi, and it's actually is Figuring the Joy of Numbers by Shakunta Devi. Okay? That's it.